Okay. Okay, thank you. Thank you for the invitation, first of all. And I've just got some message here, so I'm trying to see my way through. And yeah, my talk will be about sticky fella processes. And so what I'm going to do really in this talk is I'll present a paper which is entitled Sticky Fella Diffusions. And this paper is co-authored with David Rudman. David belongs to Open Philanthropy Project in the United States. And it was really his question which we try to answer and study first of all in this paper. And the idea here is really not to make a traditional talk using transparencies and slides and things like that. It's really trying to guide you through the paper. This has some disadvantages because obviously there's a lot of text, but the advantage is also that you'll be able to look, if interested in the topic, later in the paper and know exactly where you are, what to focus on. And therefore, in this talk, do not try to read the small text at all. Just try to focus on the things I'll highlight in the talk, and I'll tell you a little bit more about it. Then, and then we can also look deeper. So the key point is do not get overwhelmed with the text because there's quite a lot of text, but not all that is important for the talk itself, right? Maybe I should also say there are two other papers which are related to this paper, and maybe I can also try to share my screen and show you these. There is another paper which was slightly older, which is called Sticky Bessel Diffusions. Sticky Bessel Diffusions. This is already in press, and as you can see, this paper is dedicated to the memory of Larry Shepp, our dear colleague, friend, who died in 2013. And the paper will appear shortly in his volume, which will be published in Stochastic Process Applications. That is a special case of the main paper which I present, and I'll address this case in my presentation. And there is yet another paper which is related. Let me just see if I can get that. That is an older paper which goes back to a few years ago, and let me just try to do once again to show you the title of that paper. This is the paper called Stochastic Differential Equations for Sticky Brownian Motion. This paper is written jointly with Hans-Jürgen Engelbert, who also unfortunately died recently, and certainly we collaborated on this project for quite some time. And many of these things I'll be telling today originates with Hans-Jürgen Engelbert. He was really very instrumental in all of that, and I learned many of these things from him, directly from him. So in this paper, we consider these two SD systems, and this is related to the so-called Skorohod's conjecture, which claimed back in the 1980s that there is no strong solution to the sticky Brownian motion stochastic differential equation. So that is also in the background. Probably I won't be saying much about that today. Still, for those of you who are interested, you can have a look at that paper as well. So let me get back now to sticky fella diffusions, the one I want to present today. So what in this paper we are looking at the Feller branching diffusion process. This goes back to 1951, Feller's paper 1951, which also has a drift C. And it is a non-negative process, and zero is assumed to be a slowly reflecting, or I'll fairly say sticky boundary point, which means this process will spend a strictly positively measured time at that point, and we'll measure this through a stickiness parameter 1 over mu, which is a strictly positive constant. There is a reason why we write 1 over mu there. What we really want to do in this paper, first of all, we want to construct this process, and this is the first part. We'll simply prove that this process can be constructed through this SD system, which I'll comment on a little later. And we'll prove in this part that the process X fellow branching diffusion process with drift C and 0 as a slowly reflecting sticky band. The point can be characterized as a unique weak solution to this stochastic differential equation driven by standard Brownian motion B. This B is given and the rest follows then. Observe this is only a unique weak solution. And this is exactly what Skorohod's conjecture was about, that systems of this kind will not admit strong solutions. So we do not prove that in the paper, but it is a fact we proved in the paper with Hans-Jung and Engelbert, and I believe is also true here, but that was not our focus, right? I'll focus on the parameter later. You see, in this diffusion process, this B can be any real number. This is really Feller diffusion, right? Feller branching diffusion process. B can be any real number. This C is important to understand what we assume of this C, and this C will be between 0 and A strictly. A appears as a diffusion coefficient here, right? This A is also given strictly positive, and C is strictly between 0 and A. Now, when this B is 0 in this system, then this will lead us back to the previous paper on Bessel processes. Sticky Bessel processes will correspond to B equal to 0. I'll explain this connection a little later. And so the first part of the paper is really proving that there exists a unique weak solution to this SD system. I'll say a little bit about how to do that, how to prove the weak existence of this solution, right? And that wasn't really the key point. Our main point was really part 2. That was initially David Rudman's question. He's doing quite a lot of modeling for his philanthropic project, and within this modeling, he came across the question to determine the transition density function of the process X. So we are looking at the Feller branching diffusion with sticky banded behavior at 0, and we want to determine the transition density function of X. And so we will see what I want to present today here is really leading to the key point here will be to understand that there is something which I'll explain later, is a new special function appearing there. To do so, we'll be able to do so in a closed form through a new special function. And also we will see we'll need a modified Bessel function of the second kind to achieve this goal. And now when you specialize the case when B is equal to 0 to the Bessel process case, the role of this new special function played in the previous paper by the so-called Mittag-Lefler function. And so these are the interesting new aspects of these closed form solutions of the transition density function of the process. And of course, another way of looking at all of that is these are really solutions that come and go forward and backward equation. So we'll specify boundary conditions which will determine solutions to the Kolmogorov forward and backward equation uniquely. So in other words, we'll see that the sticky boundary condition can be formulated, which will single out a unique solution to the equations, right? That's also a part of what I want to talk today about. And there are also 2 papers I want to relate the results to. This is the original Feller's paper from 1951, in which he derived the transition density function in the case when 0 is an absorbing point, which means that the motion simply terminates upon hitting 0. And also there is a paper by Molchanov going back to 1967, in which he derived the transition density function when the process reflects instantaneously at 0. So which means the process really is like a reflecting Brownian motion at 0. So these are both of these cases belong to a regular boundary behavior, and they will be obtained through the limiting case. I'll explain this later on, because the general sticky case can obviously infinite stickiness means absorption, and also instantaneous stickiness means instantaneous reflection, right? And so we'll be getting these as limits in the end. And then also what I want to say, also indicate briefly, this is the A part here and B part here in the abstract, which I want to explain. These are connections to the so-called Cox-Ingersoll-Ross processes, sticky Cox-Ingersoll-Ross processes, which can be used also to model the interest rates. So we're looking at the sticky case. So this is exactly where the original Woodman's question come from. And then also this includes, as a special case, also sticky reflecting Vasicek processes, which predate the Cox-Ingersoll-Ross process. Cox process is 1985, and Vasicek was in the 1970s. And these are really well-known models for the interest rates. And so the novelty here is that we are also looking at sticky boundary behavior, which means that the process can spend some time at zero, which of course is quite realistic. For example, in Japan, it happens quite a lot. In the United States, more recently as well. And so this is an application where the result really originates from. But this really goes back to the Woodman's papers, and I won't be talking much at all about that, but I'm just telling you it is out there. We will be focusing on the theoretical part. And so essentially, here's the introduction, and the paper starts. And in the introduction, we have the question we want to consider. And this is the question whether it is possible to find a closed form expression for the transition density function of the Feller branching diffusion. In the obvious, the state space is the interval 0 plus infinity, 0 included. The process also has a drift, C, and diffusion coefficient A. And these C and A are related as that, which means C is strictly between 0 and A. And 0 is assumed to be strictly reflecting sticky boundary point, right? And the stickiness measured through the parameter 1 over mu. So that's our first question. And the purpose of the paper is to provide an answer to this question, right? And so I'll try to guide you through how to get there, right? Here is going back to Feller. Feller look at PDEs. In his case, obviously, he's got the infinitesimal generator of the process Bx plus C times the first derivative plus Ax times the second derivative, where I say A is strictly positive, B and C are real valued constants in general. I will assume throughout it that C is between 0 and A, in which case 0 is a regular, that is a non-singular boundary point. And other cases when C is below 0 and above A are well understood. So we know closed form expressions where C is below 0, including 0, then 0 is an exit boundary point, which means the process hitting 0 goes away. It doesn't stay in the state space anyway. And when C is above A, 0 is an entrance boundary point, the meaning that the process can be started at 0, but it will leave 0 never to return to 0 anymore. It will go to R plus above 0, strictly above 0, right? And closed form expressions can be found in the literature, and I quote some books here which you can find. Now the next chapter is about the history of the problem slightly. As I said, this is the paper by Feller, the original paper, 1951, in which he found a closed form expression for the transition density in the case when 0 is an absorbing or killing boundary point, and then also the paper by Molchanov again, in which where he found a closed form expression for the transition density when 0 is an instantaneous reflecting boundary point, right? Now, what's interesting about these closed form expressions is that the first includes, Feller's expression includes a modified Bessel function of the first kind, where the index is positive. Molchanov's expression includes the modified Bessel function of the first kind, in which the index is negative, right? So Woodman's conjecture was that probably a linear combination, which leads to a Bessel function of the second kind, could play a role in the solution. It does play a role in the solution, but we need more. This is insufficient for the solution, so this conjecture is not quite passing through. We need a new special function, and that was observed already in the case of Bessel process when B is 0. We need the Mittagli-Flare function, and today I'll show you we need a function which we can't describe. At least we do not know how to describe it in terms of other special functions. And so that is about the two papers. And then there was a Cox and Ingersoll and Ross paper in 1985. Simply used Feller's branching diffusion, obviously, even though it wasn't quite mentioned explicitly like that in the paper. And then also they also used the negative index as in Molchanov paper, and there's no reference to Molchanov paper at all. I think they haven't been quite familiar with developments after Feller. Right, so that is about history briefly. Now, the question of sticky boundary behavior in this setting was addressed earlier. It was addressed by Longstaff in 1992. And there is also a paper by Cabanov and co-authors in 2007, I think, where they found, they presented an answer in which the process spends some time at zero, in fact, gets stuck at zero. It means it spends a random interval of time at zero. It contains an interval, and this is, of course, not a sticky boundary behavior in the case of, in the sense of Fell's boundary classification. Which goes back to 1952, because the amount of time in that classification should be strictly positive in terms of Lebesgue measure, but contain no interval. Right? These sets are looking like a fat Cantor set, for example. Yeah. And there are also some other references here, more recent references in which the reflecting Ornstein-Uhlenbeck process, the square of the Ornstein-Uhlenbeck process is considered. This is the Vasicek model, but there was no further development towards the full Cox-Ross, Ingersoll-Ross model, which of course will be obtained once we understand sticky Fell diffusions in general, right? And that's going to be a consequence in the end, right? Okay, and so here I just describe quickly what will happen. In section 2, we'll be looking at the ASD system. We'll prove the existence and uniqueness of a weak solution. In section 3, we'll be looking at to derive the green function of X. More specific, what do we mean by the green function of X? We mean the Laplace transform of its transition density function in the time domain. Fell was looking at the whole thing in the space domain is different. In the time domain is more traditional, obviously. Yeah. Now in section 4, we'll calculate a limit at zero. I'll explain what this is. This is needed to obtain closed form expression for the Laplace transform. In other words, the green function. And then this limit will be simply used in section 5 to determine the Laplace transform of the transition density of a function of X, right, in the closed form, expressed in terms of some special functions. And here's the key point, really, which I want to emphasize, this sentence here, underlined sentence, that the latter expression for the green function, in other words, the Laplace transform of the transition density, reveals a new convolution identity for sticky laws. I believe this is more general than just applying to Feller branching diffusions. And this identity shows that the stickiness of the process, right, is entirely embodied in the single multiplication factor of the Laplace transform. So this is not surprising in view of Skorohod's conjecture, because when we will see when we construct the weak solution, we'll need to generate an independent Brownian motion to enable us to construct the process, right? And this is exactly the mysterious, deep part of the sticky boundary behavior. Essentially, you can't do it using a single Brownian motion, right? Strong solutions do not exist. You need to flip a coin independently to obtain stickiness at zero, right? And then we will also see that these new special function, obviously, we want to now invert these multiplication factor, and we will introduce new special function. Is special for us because we can't express it in terms of other functions unless b is zero, in which case the function will be reduced to the Mittag-Lefleur function. The Mittag-Lefleur function goes back to 1905, 1906. And it's proved to be extremely helpful when inverting some rational expression Laplace transforms, right? Then in section 7, finally, we'll apply the Laplace inversion. We'll see that it's possible to do vigorously, and we will apply this to the green function in general. And that will lead then to the closed form expressions for the transition density expressed as a convolution integral involving the special function from section 6. And also what we need to complete is the modified function of the second kind. And you'll see this convolution identity will reveal a connection to the instantaneous reflection and also absorption at 0, right? And then finally in section 8 is devoted to applications to the interest rate models, and especially to the sticky Cox-Ingersoll-Ross processes. A part and B part will be a more special case, which is sticky reflecting Wasserstein processes. They're used to model slowly reflecting interest rates. So I won't say much about that, but it's there for you if you're interested in that. Okay, now I'll start doing section 2 about stochastic differential equations in the first place. And here's the system we form. We want to look at this system. Obviously, B is real, C is in between 0 and A, right? And B is a given standard Brownian motion, right, appearing up there in the first line. This is ethos sense stochastic differential equation. The important thing here is that L naught X, this is the diffusion local time process of X. This is not a semi-martingale local time. Semi-martingale local times are rather useless in this setting. I'll explain this to a remark a little later. So we need to focus on the diffusion local time process, where the scaling is obtained through the speed measure, right? And so obviously, yeah, so in this differential equation, we also obviously assume that X starts at some little x, right, in the times in the state space, right? And then we'll simply ask the question of whether there exists a unique solution, right? So observe that this equation is not completely novel, because we've seen such equations for sticky boundary behavior, obviously in the past, going all the way back to the Score-Hodge question. So as you can see here, this just looks like a Feller diffusion, right? Normal Feller branching diffusion. But we are coupling this stochastic differential equation with the boundary condition. We're simply specifying how much of time X will spend at 0, but this is important to understand. This is specified through the local time, the diffusion local time process itself, right? And so now I'll lead you to the statement of the weak, the existence of weak and uniqueness of the weak solution. And to do so, I'll be going step by step, right? First of all, to recall the infinitesimal generator of the process is this, right? Clearly linear drift, linear diffusion coefficient. The key condition on the domain of the generator to be assumed is a sticky boundary condition, which is as you can see here, this is the first derivative of f with respect to scale, the scale function. And this is the speed measure evaluated at 0. And this is just the action of the infinitesimal generator of f at 0, right? And now I'll specify the scale function. The scale function cannot be quite written in the closed form without special functions here. Bessel process case is simpler, you can. Bessel process case in general is much simpler than the Feller process case here. So this is the definition, and this can be expressed in closed form using the incomplete gamma function gamma star appearing there. The speed measure of the process is given by this expression. That's quite nice, neat, closed. You can deal with it. And the incomplete gamma function is recalled here, right? And we're also imposing the speed measure at 0, at the singleton 0 is 1 over mu. Mu is the stickiness parameter, right, which is a strictly positive number, given and fixed. I just want to recall the diffusion local time definition, right? As you can see here, we are measuring the time the process spends around x, but at the same time we are dividing this time by the speed measure of the interval. That's the key difference in comparison with the so-called semi-martingale local time. And then obviously we're taking the limit when the little epsilon tends to 0. This is the local time process defined in the diffusion sense. And then what is known, it is obviously the following identity holds. The left-hand side is expressed in terms of the local time. There's the meaning of the local time. Also, what is quite crucial to understand in this setting in terms of rigor and also precision is that the local time can be taken to be jointly continuous. And there is a little quick argument here starting with this line and ending up with reference 20, which simply shows that this continuity is being reduced to continuity of the local time for Brownian motion process, And that's a well-known Trotter's result going back to 1958, right? That enables us to write the local time in this one-sided mode. As you can see here, 0 is excluded here, and likewise 0 is excluded here. That's helpful in proofs. That's helpful in proofs. And here's the basic theorem, the existence theorem. With the existence theorem 1, I just want to remind you what 2, 1, and 2, 2, 1, and 2, 2 are, because they will be recalled quite a lot. And so essentially, as you can see, maybe I can just delete some of these reds now. And so 2, 1 and 2, 2 is this SD system, right? This stochastic differential equation for the classic Feller branching diffusion. That's number 1, 2, 1, and 2, 2 is the stochastic boundary condition expressed in terms of the local time, diffusion local time of the process, right? So we have these 2, 2, 1, and 2, 2. This forms a system, a stochastic differential equation system for the process X to be found. And then the key theorem is theorem 1, which simply tells us that the system 2, 1 plus 2, 2 has a unique weak solution, right? Has a unique weak solution. We didn't prove that. I do believe that the system doesn't have a strong solution, right? Okay, now how do we do that? We simply follow the Ito-McKean construction of sticky diffusions. This goes back to 1965, really, 1963 more precisely. And so I'll just give you a quick hint on that, and I will be quite fast because I want to move on. I want to look at other things later on. And so what do? We simply start with the instantaneous reflecting stochastic differential equation for Z. This is just to be a Feller diffusion process Z, driven by Brownian motion B1, right, on some probability space, all that can be specified. And we know that this stochastic differential equation has a unique strong solution. This is well known in the case when C is between 0 and A. Here is the important connection to the Bessel process, well-known connection to the Bessel process, which means this process Z, that's the way to construct a strong solution, a possible way to construct a solution is we can connect this process Z to the process Y, and Y is the squared Bessel process solving this SDE, where B2 is another Brownian motion, right? We start with B2 and then we formulate B1. B1 can be formulated in terms of B2 as follows, right? This is a simple application of Levy's characterization theorem. And so it's well known that 214, the SDE 214 has a unique strong solution. And then you can realize Z by time and space change of Y. So we simply change the speed of time, look at the different clock. The clock is written here. The clock is written here, right? And then we also multiply, we scale it later on by the exponential in front of it. And then you're getting a Feller instantaneous reflecting diffusion at 0, right? So that's the basic connection. And so this connection is obviously translates, you can go from Y to Z and vice versa. This is because 0 is an instantaneous reflecting point. But when 0 becomes a sticky point, then this connection will break down. This is because it's a nonlinear function of time. And of course, the connection will remain when B is 0. You see, when B is 0, then in the limit, obviously needs to be understand this connection, then this term is 1. And when I pass to 0 with B, then I'll be getting in the limit, this is just simple derivative, I'll be getting Y, the process Y, at A half T, which is a linear transformation of time. And that will also be preserved when the boundary behavior of the processes at 0 is sticky. And this is why we can connect the Feller branching diffusion case in the sticky boundary behavior case to the Bessel process case only when B is equal to 0. This connection breaks down otherwise for B different from 0. And this will be reflected also in the analytic solutions as well. Right, so that's the basic connection between Feller branching diffusions and squared Bessel processes. So that's a well-known SDE for the squared Bessel process, right? And so this connection is in the background, obviously, and extremely helpful for us when B is equal to 0, because then essentially there's no difference between a squared Bessel process and Feller branching diffusion when the boundary behavior at 0 is sticky, right? And here is Ito-McKean construction, a beautiful construction. So essentially, look at this additive functional, AT, which is just normal time t, plus the stickiness 1 over mu times the diffusion local time of Z, the process Z at 0, right? The diffusion local time process Z at 0 is defined in the same way as before. This AT is strictly increasing, continuous, nice additive functional, and therefore I can look at its inverse. And this inverse will be a new clock. So now we see what exactly is the meaning of this new clock. You see, when your Z is away from 0, if this process Z is away from 0, then the local time is constant, it doesn't increase, but this L doesn't increase. And then therefore the A runs as ordinary time. T is just AT is T then, and then the inverse of A is just ordinary clock, ordinary time, which means this T becomes then ordinary time, right? But when Z hits 0, when Z is at 0, then the local time in the neighborhood of 0, infinitesimal neighborhood of 0, then the local time starts increasing. This local time will increase, and therefore A will go faster up. It will increase faster than normal time. This L will increase as a function of time. Therefore, it will enlarge the normal time, and therefore this new clock will go faster. Therefore, its inverse will go slower. Yeah, which means capital T as a function of little t will go down. It will slow the normal time, and the effect of this time change will be that the process is followed by this clock, as we do. This is now here, so which means we are looking Z process with this new clock. Sorry, I need to use a rectangle here. The process Z with this new clock will somehow spend more time at 0 because the clock slows down, right? And that is my process X to be. This is obviously rather intuitive, and that's the heart of the matter of the Ito-McKean construction. By the way, Feller discovered sticky Brownian motion. In my view, that was his greater discovery in mathematics in general, right? The sticky boundary behavior. The fact that the second derivative plays a role as well, in addition to the Dirichlet, Neumann, and Robin problems, right? The second derivative at the boundary point describes stickiness, but he never actually understood himself how to construct such processes, and he tried. If you look at his papers, 1952, 1954, 1957, the three major papers on boundary classification, he was trying really hard to get there, but he didn't quite succeed in doing that. He managed to construct elastic Brownian motions by Robin conditions. He understood that. He understood that the local time would play the role, but it was only Ito-McKean who managed to do that. And now the rest, once you define this process X as the time change of Z, instantaneous reflecting Z, which slows down at 0, now the rest is really a matter of routine to calculate the certain things and verify that these X so defined obviously will solve the stochastic differential equation in the weak sense. Why in the weak sense? Because we're making use of Dubs-Martingale representation theorem by generating another Brownian motion B naught independent from B1, and then this B naught is used in addition to time change B1 to define this new Brownian motion. And so you can see from this construction that extra randomness enters the scene. And the Scholar-Holt's conjecture was that this is not possible to do without the extra randomness. This is exactly his conjecture going back to the 1980s, a deep conjecture, which was later on proved to be negative indeed, that it's not possible, right? We haven't proved that yet, but we'll see later on. And this is actually our question later on. In analytic terms, we'll be looking for this extra randomness. How do we specify this extra randomness analytically? And we'll see that that will be obtained through the green function, right? And so now, having that in place, if you define this B, then you can verify it. Standard Brownian motion by Levy's theorem, and then really your X solving an SDE will be your solution to the SD. This is 223, can be verified. And likewise, the time spent at 0 will be equal exactly 1 over mu times the diffusion local time of X, which means this is a solution to your problem, right? Which means this is a proof that the SD system has a unique has a weak solution, right? Has a weak solution. And now in part 2, we'll now prove that the solution is also unique, right? That the law of the solution is uniquely determined this way. And this bit I really learned from my the friend Hans Jürgen Engelbert. For him, this is that was really his thing, right? He was doing these things inside out. He knew all the tricks and all the subtleties of these kind of things. And so what do? Really, you simply undo the previous steps. You go backward, right? You define your TT in terms of as this additive functional. Then you look at the inverse of this additive function. You need to be careful here a little bit because t in general at infinity is not necessarily plus infinity. It could be also a finite point in principle, but later on you'll see it's not the case. And then you simply you have your solution x, and you simply time change this solution x to the process z. And then you prove that this process z, simply looking at the SD back, and then you prove it, and so you observe this martingale here. You observe that the martingale has the quadratic variation equal to the length of time. Therefore, by Levy's theorem is standard Brownian motion, which I'll call W, right? And then this Z solves the SD driven by W, right? And then you recognize this SD to be exactly the Feller SDE, right? The instantaneous reflecting SDE. And therefore, this SD has a unique solution, a unique strong solution that's important, right? In other words, Z is a deterministic functional W. The Z will be a deterministic functional W, right? And then you simply play with the rest. You go back in time, and then you look at your AT, what it is by definition, and then you analyze your local time, and then you get the following identity for A, the one we started earlier. You see AT is t plus 1 over mu LT naught of Z, which means A itself is a deterministic, it is a functional of Z, and Z is a function of W, right? The Z is a function of W. Therefore, therefore A itself is a functional of W. This A will be a functional W through Z. And then TT is the inverse, right? TT is the inverse of AT. You also establish here that this cannot happen, right? What we really have, the T infinity is infinity. And therefore the whole thing, the equations are really satisfied on the entire real line, R plus timeline. And then TT is the inverse. And then you go back to X. Then you see that your X is equal to Z at TT. TT is a function of W, and so is Z. And therefore X is a deterministic, well-determined deterministic functional of W. W is the Wiener process, a standard Brownian motion process. And of course, this is true also for other time points. And this really tells you that the law of X is uniquely determined. The law of X is uniquely determined. So therefore, then you don't have only a weak solution. That could be, and this weak solution is unique in law, unique in law. But that's a very nice derivation, which I enjoy doing with Hans Jürgen. In fact, he really showed me the subtleties of this, right, at the time. Now, remark 2 will be that simply tells you that the process X constructive is a regular diffusion process in the sense of Eaton McKean, in the sense of their book. And here is a little remark which will tell you that the semi-mounting local time would be useless in this setting. Why is that? If I look at the semi-mounting local time of Z, of my process Z, remember Z is the instantaneous reflecting Feller branching diffusion process, then I claim that the local time, the semi-mounting local time is equal to 0. Right, so it doesn't develop really. This is because if you look at the quadratic variation of this Z process, it is just Z SDS, right, in the end. And then obviously this Z is below epsilon, and therefore I can cancel this little epsilon, right, with this inequality. Clearly the local time itself is non-negative, and then by canceling little epsilon there, I'm getting actually just the length of time here. which of course is equal to, in the limit, to the length of time of Z spending at 0, which is 0, because Z is instantaneously reflecting at 0. So which means that the semi-mathematical local time is really can't be make any use of in this setting, and we are really forced to go to a diffusion local time. Yeah. So that is section 2 completed. Sticky boundary condition will be to look at the Kolmogorov backward equation and forward equation as well, associated with the process X. Obviously, X is a nice, strong Markov process, Markov in general, and a continuous, and therefore Kolmogorov forward and backward equation can be written down, and this is what we'll do now. And then we'll obviously ask the questions, how do I characterize the sticky boundary condition for these PDEs, right? And here is first of all the definition of little p. This is a transition density with respect to the speed measure. It's nicer, better behave. You'll see also some examples later of this kind of claim, and that's the meaning of it, right? So I integrate with respect to the speed measure. Then obviously I can go to little f, which is p times m, the density of the speed measure, and that becomes then the density, the transition density function with respect to the Lebesgue measure, little f, right, of the process, right? Then of course this is true for all measurable A, strictly contained in A plus infinity. A is excluded. We can't measure A because A is sticky there, right? But outside A, F will do the job as a standard transition density function. And then we can recall, of course, in this setting, Kolmogorov backward equation first is written here, right? Together with the initial condition, which is written in the weak sense here, through the weak limit, because the process starts at little x, and therefore is going to be Dirac measure at little x in the limit, right? This can be specified in terms of the probability distribution functions exactly. Then we can also look at the Kolmogorov forward equation, which in this case is the adjoint of the first equation, which is ft is minus b mu partial derivative y plus 1/2 sigma squared f y. So that's an equation, a PD for x given fixed, right? And then of course the same boundary condition holds there as well, because the process starts at little x, right? And this b obviously b is linear, and sigma is also is a root of y in general. Well, for the fellow branching diffusion, right? So these are Kolmogorov's equations, and of course the equations themselves with these conditions are insufficient. We can't use this equation with the initial condition, either backward or forward, to specify, to find the transition density, because we need to know the boundary condition 0, which will specify a sticky boundary behavior. And so what I'm going to do in this section here, I'll simply derive these sticky boundary conditions. And the approach will be through the green function of little p. Observe little p, this is transition density with respect to the speed measure. It's nicer because it's symmetric both in x and y. And also it applies on the entire interval 0, 1, the state space 0, 1, 0 included, right? So it's well known that the green function is explicitly expressed in terms of phi and psi. Phi and psi are two functions which solve. The phi function is an increasing continuous function, in fact C2 function, solving this boundary value problem, where the first equation is just the infinitesimal generator equation, right? And phi is increasing, right? And we also assume sticky boundary condition. This is how we'll get a sticky boundary condition to the PD, because we'll couple of them together to the Laplace transform of the green function, right? So that is phi. Phi is increasing. So normally in literature, people write phi is decreasing and psi is increasing. I always get confused about it. I prefer to call phi increasing, phi first, psi second, phi increasing, psi decreasing. And so this is the reason that I use phi to denote increasing solution. And then similarly, psi is decreasing solution. Psi is decreasing solution, which means we have the following system. Now, the first two equations, this is the infinitesimal generator equation, obviously, for psi. Psi is decreasing, and here we have a normal condition, normal in terms of boundary behavior at infinity, because plus infinity is a normal boundary point for the process, and these are the conditions we need to be assumed there, right? This W appearing there, the W appearing in the denominator here, both places in the green function. This is the Wronskian. The Wronskian is also defined in terms of the scale function derivative of the Wronskian of phi and psi. Yeah, and then also psi and phi, they have both probabilistic interpretations in terms of the exponential function of the first heating time tau c to point little c. And similarly, this also holds there. And this is important because this proves that phi and psi belong to the infinitesimal generator domain, and therefore the condition 312 in particular is indeed to be assumed that it will hold because the function belongs to the domain of the generator. And now we simply in part 4, having stated all these facts, which I'll use a little later, in 4 I'll simply derive boundary conditions for Kolmogorov equations. We'll start with the Laplace transform of little p, the green function, which is given in this form. And then what we're going to do, we're going to differentiate both sides of the previous identity. Again, we need to also pay attention to sufficient conditions which will enable us to, for example, to exchange the derivative in the integral here. And if you do so, and if you now proceed by knowing everything you know, then you'll be getting this is the result as the first step. And then what you do now with the rest, obviously this lambda is appearing in the final term. So this lambda is appearing here. Obviously, this hinges to the Laplace transform, and then obviously the integration by parts should be applied for the final term. And if you do so, you're getting the following identity. And then if you combine the two identities, this one and the previous one, you're getting the following identity. And then the uniqueness of the Laplace transform will tell you that the integrand after the exponential should be 0. And this gives you the boundary condition, the sticky boundary condition for your PDEs, right? And so observe that P is linked to F. If I know P, then I also know F because I know the speed measure density. So this can be reformulated in terms of F. Right? I'm not doing it here because we won't make any use of these conditions later. I'm just saying that it's possible to do that. And then by symmetry of P in both X and Y, I get another condition. Observe this derivative is taken with respect to the scale function. So this is a sticky boundary condition. Both of these are sticky boundary conditions which need to be added to the Kolmogorov backward and forward equation respectively, right? And then also normal conditions at infinity, something similar can happen, can be made there, is this one. We start again from the green function. Then we differentiate, well, we first observe that P at infinity must be 0. This is 315. This is because psi satisfies this condition. And similarly, the first derivative with respect to the scale function, psi also satisfies this condition, will give 0. And then that gives you, by the uniqueness of the Laplace transform, the following two conditions, natural boundary conditions at infinity. And then by symmetry, you're getting also the other one in the Y domain as well. And so if you now summarize what you've done, you simply, if you now remove all these reds, so essentially what I claim now is we've obtained the sticky boundary condition. Let's see where I am now. The sticky boundary conditions at 0 for little p, and also the normal natural boundary conditions at infinity for little p. And then recall that p and f are linked in this way. M is known. And then therefore this gives you boundary conditions for f in Kolmogorov forward and backward equation. And indeed, under these conditions, it's possible to see that the equations will have unique solutions. And then we simply do not do that in the paper. We're not going in that direction because instead what we're going to do, we will simply look for explicit forms for these solutions in the case of the sticky branching diffusion, right? That's why we stop here, but it's possible to do that as well in the PD theory as well. Now, here is now the limit of 0. I want to explain quickly. We are solving the systems I showed you earlier. These are the systems 310 plus 313. Let me just go back to remind you, because there's been so much already. What are we looking at? What we're trying to resolve now, solve explicitly. These are the systems. Right? Let me just remove some of these reds if I can. Yeah, here we are. So here we'll now focus on 310 to 312. This is the first system for phi, and this is a system for psi. Phi and psi form the green function, right? The green function we are after. We want with the green function as explicit as possible. So now I'll be simply trying to see to what extent these systems can be solved, in which way can be solved. And here is this comes the limit of 0. Now, if you look at this differential equation in both cases, both of these systems, this is the equation of this kind. Now, when b is 0, then the equation can be solved using the modified Bessel process of the first and second kind, and that has been done in the Bessel process case earlier. So this is a less interesting case here, and therefore this is explained here in this text. Is explaining this connection. So I won't be focusing on that at all here now. Instead I'll be looking at b is different from 0 case, and then passing to the limit we'll also obtain the previous case, right? Now the two solutions are F1 and F2, which are expressed in terms of comma, Confluent hypergeometric function M. Yeah, like that. So these are two linearly independent solutions. And using these two linear independent solutions now on the underlying asymptotics, essentially we are guessing now the solutions to the two systems. And here I am, 4, 7 will be a linear combination of F1 and F2 above, and psi is completely guessed fully as a particular linear combination with these coefficients, and this turns out to be U function. U function, some of you will recognize this is Trichomi's confluent hypergeometric function, which is defined in terms of M's as follows. So that will do. For the first system. It will lead to a solution to the first system, a unique solution up to a positive constant, right? Similarly, for the second system, we will be also guessing solution in terms of linear combination and actually pointing out explicitly the second solution psi, the decreasing solution psi. But now, what's really surprising, what came as surprises us, is that it is no longer Trichomi function. It's a modified function. We can't do it with the Trichomi function for some asymptotic reasons at minus infinity through the real line. And then we are getting U tilde function, which is a slightly different linear combination of this kind, still explicit, still doing the job, right? And so now what you really want to do, you want to specify these, we have 2 degrees of freedom, alpha and beta. This psi is definitely the one you want. You can verify all of that. And alpha and beta will be determined now, and they'll be determined through the limiting behavior at 0. You see, I'll be looking at the sticky boundary condition, and then observing that what I really need to calculate is this limit. The limit, this is d phi over ds over phi at 0 in the limit, and it turns out there's a nice closed form for that, which is this, expressed in terms of parameters. And the proof is simply using some properties of special functions of this kind and passing through quite comfortably and getting there. And then this limit then therefore enables you to express beta in terms of alpha, the 2 unknown coefficients, and therefore everything is now one-dimensional as it should be, right? And now having this in place, you can determine the Laplace transform, right? The Laplace transform, and here it is. We first start with the sticky case, a new case, not considered earlier. This is the Laplace transform in the sticky case. In other words, the Laplace transform, or equivalent to the green function g of x, can be explicitly expressed in terms when the speed measure at 0 is strictly positive and strictly finite, as follows. We have 2 cases, in fact 3 cases. First, when beta is negative, then the Laplace transform is equal to, the green function is equal to this. Observe you have m times u, and then u times u appearing there. and then the rest. It is a bit technical, but you can't avoid it, unfortunately. And the second case, B case, is when B is 0. When B is 0, this is back to the Bessel process case. We know it. We know it already from before. The green function is given now as the multiple of I and K. These are modified Bessel functions, and also K later on. And now observe, this is exactly why Mittag-Lefler function comes in, because of this rational function. The inverse Laplace transform of this rational function will be exactly a modified Mittag-Lefler function, right? Then this kappa constant is expressed in terms of the other constants as follows. And then finally, the third case is when beta is positive. I'm getting a multiplication of m and u tilde to form a green function, and then also u tilde and u tilde. No longer you can use here, right? Proof, really combining all the previous facts, putting it all together, calculating Wronskians and all of that, putting it together. It's a bit cumbersome, it can be done. There's a first case. Number two case, similar. You can also go back to the Bessel process case, as I said earlier, by passing to the limits when b is 0, and read it from there, right? And then finally, the third case is similar. You are simply looking at the Wronskian, calculate the first one, the second one, and so on and so on, and put all these together, and you're getting these closed form expressions. Now, so what? We've got the closed form expressions, but can we invert them? That's the question, right? Can we invert these closed form expressions? That was a difficult question, right? And so before I get there, let me also state Laplace transform in this instantaneous reflecting case. This corresponds to Mulchannel result. Again, three conditions: B negative, right? B negative, G is given explicitly as M times U, right? And then when B is 0, G is given explicitly as I times K. These are modified Bessel functions. And then finally, when B is positive, I'm getting the Laplace transform, the green function, to be M times U tilde here again. See, U tilde is creeping in. Again, straightforward verification. And then also fell as original case, absorbing case. Again, three cases: B negative, B 0, and B positive gives me M times U, right? And then I'm getting also here just I itself. This is the original Fell expression, right? And then also G, which is M times U tilde, right? Okay, proof, again, you put everything together, and here we are now. You see, this is what I want to focus on. Now, why these additional expressions are important to us? Because if I go back to the sticky case, and I'm interested in this sticky case, really, right? So if you look at this sticky case, proposition 5, Laplace transform in the sticky case, then what I really want to do, I want to look at the Laplace transform and want to invert it. Right, I'm getting M times U function to invert that. It's not so simple, actually. So these expressions are not tabled, right? If you look at tables of Laplace transform, they are not there. Similarly, M times U tilde, U tilde, U tilde. They're not tabled, but nonetheless, by using these Laplace transforms, which we obtain later in the instantaneous reflecting case and the absorbing case, this is now possible. It turns out, if you really read these expressions carefully, if you spend some time with it, because it's quite technical, then you'll recognize there is some beautiful decomposition happening there. This is corollary 8. Corollary 8 is the convolution identity for sticky laws. And now G is my sticky green function. A is my absorbing green function, Felles, and GR is the green function of Molchanov, instantaneous reflecting. You see what happens? You're getting the sticky function. Now it's you need to trust me, right? Because this is the original expression I showed you. It's very lengthy, long, but you can simply recognize GA creeping in like that, and then you're having this difference: GR minus GA times some magic L. This L does the job. So essentially, from GA and GR to GS is L. L does the job. You see, L is a multiplying factor. If I invert this, then I can use the convolution theorem. Right? There's the idea. And now look what L is. L is really interesting. For those people belonging to special function theory, they'll like it a lot. First of all, when B is 0, this was understood in the Bessel process case. L is just, you see, a rational function of lambda. It's a Laplace transform. You know how to invert that. We are inverting these functions, rational functions of this kind, using the Mittag-Lefley function. By the way, the Mittag-Lefley function is not in Edely's book. It was only reinstated in the literature back in the 1990s in relation to the so-called fractional calculus, proved to be useful there. But this case is quite well, you can invert this, right, in terms of the Mittag-Lefley function. But the other cases, these are now truly branching cases when B is negative or when B is positive. These are truly fellow branching diffusion cases. You're getting this is just a constant here, constant, right? And this constant is written here in this case, right? Explicit, right? And so what you're getting actually the ratio of two gamma functions. The ratio of two gamma functions is quite a nice topic for. It was investigated quite a lot in the special function theory. Over many, it's still being investigated, you know. And so essentially, we want to invert the ratio to gamma functions in the denominator, right? And similarly, when B is positive, similar expressions appear there. Again, the ratio of two gamma functions appearing there, and that is forming my L. That is forming my L. As I say, kappa is fully specified, this constant, right? And so therefore, to invert this Laplace transform, we want to understand L itself as the Laplace transform, and this is now what's being done to this special function I introduce. I'll be a little bit quicker here. And so essentially what we want to do is this, we want to invert, we want to find capital F solving this equation. As you can recognize now, alpha is a constant, right? Which can be specified, and then you have the ratio of two gamma functions, right? And so,
excuse me, please, but we have only 60 minutes for the talk.
60? So,
yes.
Okay. I thought that we started 2. No, okay.
Or 2 minutes.
Okay, all right, okay. Sorry, I thought that you still have about 10 minutes, but anyway, okay. So you can see here, I'll conclude in 2 minutes. Then this is the Laplace transform, and then you can simply go to the there is a theorem by Churchill which is applicable. You can write down the inverse Laplace transform. You can use the contour integral representation for this, and this is what it looks like. You see that is this is the modulus of L, which you want to invert. And then Jordan lemma is enabling you to actually calculate, and also the simple poles are these are, you see, simple poles exactly, but you have this explosion here, right? Simple poles are happening there. This is a negatively line, right? All of them. And then I need to really be fast. You can calculate the residuum, and essentially to cut the story short, we can express this function in closed form using zeros of the gamma function. And I think that I've written somewhere in front. These are the lambdas are zeros of these gamma function. That's all you need to have. Right? These lambda n solve this transcendental equation in terms of the gamma function. Once you have lambda n's, then you can simply form the function f, and then you have a full inversion possible. This is also these zeros appearing there. This is also interesting, useful for the proof when you're using the Bromwich integral to represent that. And that's a general case of this f. That was the previous case was when b is 1. This is the general case. And then also positive and negative cases when b is -1 or 1 are related in this way, quite nice way. And that's the function. It doesn't look very exciting, but there's the function f, right? There's the function f. And then this is also a connection to the Mittag-Lefley function, which is here. And then once you have this function, you can calculate the inverse Laplace transform. And this is now done first at all in the absorbing case. I will not go to this expression because that's known. Then also the inverse Laplace transform in instantaneous reflecting case, you can calculate explicitly. And then finally, the Laplace transform in the sticky case, which is exactly the convolution identity expressed in terms of f, capital F, and then the rest is explicit. The rest is explicit. This is the case b positive, b is 0, that's well understood in terms of the Mittag-Lefley function. And then this is a genuine picture of the transition density obtained in this way, a little p, right? As you can see here, the process starts at 1. This is why I have singularity there initially. That is the case which corresponds to b equal to 0, right? It's well known in the case of Bessel process in particular. And then the first case, sorry, the first case, just to make it clear and conclude, the first case was the case when b is different from 0, different from 0. And then finally, we are getting also the interesting point. We can calculate the atoms at 0. The process at time t is at 0, the strictly positive probability. This little p calculated explicitly in terms of f. And then here it is, the atoms at 0, right, for the process expressed explicitly in terms of these f, which you know. And there's the also f doesn't, little f doesn't integrate to 1 because of the sticky boundary behavior. And here is really the probability the process spends at 0. As you can see, it has this funny shape, right? And there are also applications to the interest rates. And here I stop, right? Because I need to stop. Sorry, I thought that it's going to run all the way to the full hour. Yeah, but anyway, you got the idea, I guess. Okay, so thank you.
Thank you for your so informative talk. And dear colleagues, please, your questions.
Sorry.
Maybe some comments.
If I look in your equation 231, there is no mu. How the mu appeared in the solution?
Sticky Bessel diffusions. Just a second. Sticky. Let me just.
There was no mu in the equation. It's in formulation of the equation.
Okay. Which equation do you want?
31.
Okay.
How does happen? Yes, so
yeah,
31, I think. Yes.
Oh, sorry. I need to go forward.
Is this question also? No, not in this, but in the previous one.
231.
There is no, yes, in this equation, there is no mu. The last expression, last 231. Yes.
Yeah.
231. The last formula.
Oh, no. This has nothing to do with mu. This is just instantaneous reflecting process.
Okay, thank you.
This is so what happened in the proof. So I don't know if I can remove all these words. It would be easier. Quite a few of them. Okay, so what happens in the proof? This is the proof of uniqueness of the SDS system. So what do we say? We simply say, okay, let X solves the system. Let X and B solve the SD system. And then you simply define TT to be this expressed in terms of X. AT is the inverse of T, right inverse. And then Z is defined as X time changed. You see. So in principle, this X, in principle, this X contains this mu, but when you time change it with A also contains mu, the two cancel, and then you simply see that the Z solves this stochastic differential equation driven by standard Brownian motion W, and mu is irrelevant anymore because it's just a standard branching diffusion process of Feller when 0 is instantaneously reflecting. Yeah.
Thank you.
You're welcome. Yeah.
Thank you.
Dear colleague, maybe another comments or questions?
Goran, I have the following question.
Hi,
so
Albert.
you prove existence, you prove existence of the weak solutions, but what about strong?
It's what we proved what we proved in the paper with Engelbert, right? This is the in the paper with Engelbert.
So why no strong solution? For example, in examples of Tanaka, it's clear. Why not? But you prove a weak solution and you use additional randomization in the zero. And
that is true, yeah. So you say we didn't do it in that paper now I showed you today, but we did prove that there is no strong solution in this paper. This is a stochastic differential equation for sticky Brownian motion. This is simpler, right? And so we simply prove that if you look either sticky Brownian motion at 0, which moves freely in the entire real line, or sticky reflecting Brownian motion, we prove that both of these systems have a unique weak solution, in fact, jointly unique weak solution. And also we proved in the paper that there is no strong solution. There's a full proof of that.
Okay. Second question.
Yeah.
I know one very good application of the sticky processes.
Yeah.
And in fact, I began to do it, but I didn't finish. The problem is the following. Let's consider Black-Scholes model.
Yeah.
It's a geometrical Brownian motion with two parameters.
Yeah.
But now they calculated rational price.
Yeah.
But now let's suppose that there is a level A equal to 1, such that above this level we have one geometrical Brownian motion with parameters, some parameters, but in the rest part below, you have another geometrical Brownian motion with another parameters.
Yeah.
And so where is the level? Problem is how to calculate a rational price.
Oh, I see.
You understand?
Yeah, I understand.
And so, and so suppose that you have financial model.
Yeah.
If price is such very big, you have one, have to say, moving process. But if price is small, you have another one. You need to calculate rational price. Goran, it's a very good problem.
I agree. It's an interesting question.
I began to calculate it.
Yes.
But I didn't finish.
Okay. Yeah, it is an interesting problem. Even the scale function will probably not be different. It depends if the drift is changed only or the diffusion coefficient is changed as well. Then maybe the scale function won't be differentiable at that point. So this is really
maybe you know some works, papers about this, but I didn't know.
No, this is I think this is related to
no, okay, we shall discuss it.
Yeah, we can, definitely. Yeah, we can. Yeah.
Maybe another questions, please.
Maybe I ask, is it known something about numerical schemes for such type of equations?
Yeah, that's a good question. My co-author, he is very much numerically orientated, and he studied this deeply, right? And one of the reasons he asked this question is exactly that he wanted to be able to calculate transition density functions directly without appeal to the numerics. I understand it. It's for him. He also thought that that there should be more efficient ways to do it numerically, and he tried to develop some of these arguments because he calculates quite a lot using computers and things like that. But the conclusion was it was inconclusive in the end. We do not know. So yeah,
thank you.
You know, definitely these are interesting questions, you know, and so I feel what we've done in this paper is it has a more theoretical value because this function, which simply it was served to this convolution identity. Really, we didn't really invent the ratio of two gamma functions. It just came out, right? So we want to study it in terms of special functions, obviously theory. But when it comes to numerics, we can also calculate things. We can calculate the transition density. I showed you these are genuine pictures using this function, but I'm not sure if this is the fastest way of doing it, because he knows about many other tricks and possibilities, and that was his claim as well. He thought that the things could be made much faster. Yeah. So That's an interesting question. Unfortunately, I don't know much about it, but I know that it is definitely interesting for people applying these results. For him, in particular, yeah, yeah.
Thank you.
You're welcome. Yeah.
And I have a few questions.
Yeah.
First,
yeah.
Do you consider transition probabilities P, T, X, Y when T, for example, tends to infinity and Y minus X tends to infinity? And of course, it's the connection between T and the spatial coordinate.
You mean whether we consider asymptotic? So.
Ah, of course.
No, not. I'm trying to understand your question once again. So, can you maybe repeat once again? I'll try maybe get the. So yeah, this is our little p, right? This is the transition density with respect to the speed measure.
Yeah.
And then we have also little f, which is the transition density with respect to the Lebesgue measure. That's the meaning of little f. And that's the meaning of little p. So we know that little f solves uniquely Kolmogorov backward and forward equations when we add these sticky boundary conditions. So what is your question? Whether we consider the asymptotics or?
I think it's, I would like to ask about maybe 3.19.
Oh, okay. Okay, let's go there then.
Um,
19. That one. This is just the.
No. For example, or 3.18. In such situation, what can you speak about the transition PTXY?
You mean that one?
Yeah.
That is found later on. So we have a closed form expression for this function, right? Oh no, sorry, generalized. No, I'm showing you a wrong paper right now. Just a second. I'm showing actually this is a different paper. I'm showing you. I want to go there. So your question is, what is this p equal to, right? And the answer is really the final theorem there, right? In the we find first the Laplace transform, and then we invert this Laplace transform. And
I
so,
would like to
yeah.
understand. We can
Here it is.
Yeah.
So here is the sticky boundary case. It is the. Just a second, maybe it's hard to find it. This one, yeah. So here, this function is given like that.
Yes.
So it's explicitly given as this. Yeah, so you can argue it's not quite explicit because we've got one integral here, right? You know, but
easy.
Well, yeah. So it's hard to integrate, right? But maybe it's possible to express this differently, right? But certainly, see, this f comes here. If I know this f, which is exactly the inverse Laplace transform of the ratio of two gamma functions, and I represented formulae for this f. So it's like a new special function which we're trying to study. Then this is known, you know that, and then the exponential and k is just Bessel function. So you multiply this f by these two, and you integrate, and then you add all of that, and then you get in closed form. And this is exactly your p. It's exactly your p.
For example, we consider the branching random walks on discrete structure, for example, the dimensional lattices with continuous time.
Yes.
And in that situation, of course, there are some connections between your result and maybe the result when we consider such processes on discrete structure.
Yes, definitely, yeah.
For example, in our situation, the lambda, you consider the Laplace transform from transition probability.
Yeah.
And in statistical physics, they consider the situation as in works in Ushiyama with lambda is But when we consider more difficult process,
Yeah.
the rho lambda is eigenvalue of the equations of Kolmogorov backward equations that, for
Yeah.
example, which describes the mean number of particles or something.
Yes.
So I would like to understand such connections with such result. And for
Yes,
example, it's the Mittag-Leffler distribution in situation when the, for example, when we consider the random walk with infinite variance of jumps.
Yes.
Only not branching random walk, random walk with infinite variance of jumps.
Yes.
And such situation in for recurrent random walk. Such situation we get Mittag-Leffler functions too.
I see. Yes, yes. It's interesting. Yeah.
So thank you very much for
you're
your
welcome. You're welcome. It's a great pleasure for me to give a talk on your seminar. Yeah.
If you can, could you send me or your the last paper for report?
Oh yeah, it's online. It's online. You can, if you just type in my name, it's online. All three are online.
Good.
Just Google my name and then you'll get it. You know, it's out there.
All publications and or in archive.
No, I don't put my papers on archive. In general, I do sometime, but I didn't put these ones. You know, I just keep them on my website. Yeah. But if you just, I can do it if you want. I can email you the connection. But if you just Google my name, you'll get them immediately. Yeah, all three of them. Yeah. It's easier that way. You know? So, you're welcome. Pleasure. Yeah, as I say. Yeah.
Maybe in other questions.
Yeah, sure. Of course. I'm very happy to try to answer any question, really, if I can.
So now we can finish our very interesting seminar, by my opinion. And I would like to say a few words about our next program of our next seminar. We will have a talk of Ivan Vysotsky. He is the head of laboratory of Moscow Center of Independent Continuous Education, and he will speak about the coupon collections problem. Such problem were considered in the middle of last centuries, but Ivan have a few new results in these directions. So I hope to see everybody on the next Wednesday. Goodbye, and we can finish our seminar.
Okay, thank you. Bye-bye.
Bye, everybody.
Ciao, Goran.
Hi, Albert. Bye-bye, Albert. I'll take my plane back.
It was very pleasant to meet you, at least to see.
You too, Albert. You too, Albert. Yeah.
Okay, bye-bye.
Okay, bye-bye. Bye-bye, everyone. Bye-bye.